So today we're going to start talking about the concept of a limit. All right. And I'm going to start talking about concept of a limit with something that isn't exactly what it is, but like close. You guys see this sequence? We start with a triangle, and then there's like a pentagon, and then I don't know how many sides. We're getting more and more and more sides. As we add more sides, what is this figure getting closer and closer and closer to? A circle. That is correct. Will it ever equal a circle? No. Because we can't take straight lines and all of a sudden curve them and make it have no vertices. You know, with a triangle, it's got 3 vertices. Pentagon has 5 vertices. We can have infinitely many vertices, but there's still going to be little straight lines between all of them. So it'll never actually be a circle, but it's getting really darn close to a circle, isn't it? So this is kind of what a limit is, where we are looking to see what we are approaching, but not necessarily will ever equal. Okay? Here's a couple examples of using the notation of limits and actually me finding the limit using this picture. So when it says find the limit is the y value. The limit is y value. So this is saying find the limit as x approaches 2 in this function that's given here. Now, you won't always have a graph right now. First time you're seeing limits, I have a graph for you right now. So in order to figure out the limit in which x approaches 2, in order to figure out the y value in which x approaches 2, with my graph right now, I'm going to look at just the limit where x approaches 2 from the left. And to say from the left, I put like this tiny little negative sign that looks like it's an exponent, but it's not. And I'm just going to use my picture for this, but we won't always have pictures. So I'm going to start the left, and I'm going to go through my x values. So like x is -2, x is -1, x is 0, x is 1, x is... So it's not going to ever equal 2 because there's a hole in the graph. But as I am going from left to right, as I'm coming from the left, and x is getting closer and closer and closer to the number 2, what is y getting closer to? 4. That is the limit as x approaches 2 from the left. Now I'm going to do the limit as x approaches 2 from the right, and I show that it's coming from the right with a little plus sign. We always write the equation after the limit. You don't just write limit x approaches 2 plus. That's not a complete thought. Now I'm going to start on the right side, and I'm going to, go through the x values here. They're like past 2, 2.4, 2.3, 2.2, 2.1. What are the y values approaching as x is getting closer to 2? It's too easy. You think you're wrong. Come on. 4. So I can conclude if I have the same answers for both the left and the right, I can conclude that the limit as x approaches 2 of x cubed minus 2x squared over x minus 2 is, in fact, 4. Mind-blowing, huh? That should seem very easy. Did it seem very easy? Is anybody confused? Not yet. Okay, so the next one, I have another graph. I did not write the equation, but it would be a piecewise. And in calculus, you do use a lot of piecewise functions. So I just wrote f of x for the equation. Excuse me. So we are looking to find where x approaches 1. What the y is when x approaches 1. So I'm going to do the limit of x approaching 1 from the left of f of x. So I'm going to start on the left. I'm going to move my x's so they're getting more and more to the right, to the right, to the right, until I get to almost to 1. What y value are they approaching? -4. Is that what we said? Yeah. And then we'll do the limit as x approaches 1 from the positive, from the right of f of x. So I'm going to start on the right, and I'm going to approach 1. I'm approaching 1. I'm getting close. And what number do I get for y? I get 3. These numbers are different. If the numbers are different, the limit does not exist. So now you know what they were talking about in Mean Girls the whole time. If you don't know what I'm talking about, you got to watch the movie. Do you know what I'm saying? Oh. She says the limit does not exist. Yeah, the math. She wins the math contest. Okay. Here's without a picture, using an equation. We're going to determine the behavior of this rational function. This is more of what we're going to use it for today. Today we're studying rational functions, by the way, but I have to teach you what limits are. So those are the two things we're doing today. Excuse me. I see this rational function, and what I'm going to want to do every single time we have a rational function is factor it. Okay, so I see something. Is it factorable? X minus 1, x plus 3 over x minus 1. If I have x minus 1 in the denominator, what does that tell me about my graph? The x cannot equal 1, right? That's telling me my domain does not have a 1 in it. So here in my table, at x equals 1, that's undefined. There isn't a value there. Now, another thing that I notice is there's an x minus 1 on top and on the bottom. So I can cancel those. And then when you did this in algebra 2, you would write x plus 3 where x does not equal 1. So you had to include that domain restriction. So now what we're going to do is we're going to figure out the behavior of the graph around this missing piece. We're going to find the limit as x approaches 1. So we're going to find the limit as x approaches 1, and we're going to do it from the left. And then over here, we'll do the limit as x approaches 1 from the right. So what we do when we're trying to find, without a graph, we're trying to find what y value is, we're going to choose numbers that are around that number 1 that are like really close to it. So You don't have to choose these numbers. These were chosen for us. We're just going to use them. If I plug in 0.9, and I'm just going to use this equation after it's simplified. If I plug in 0.9, what will I get? 3.9. If I plug in 0.99, I get 3.99. If I plug in 0.999, I get 3.999. What are we getting close to? 4. The other direction, now I'm going to plug in 1.1, and I get 4.1. I'm going to get closer to x being 1. I've got 1.01, which is 4.01, and then 4.001. What are we getting closer to? 4. So the limit as x approaches 1 to this equation would be 4. So we're going to start rational functions today. And there are a couple of rational functions that you have seen or that you see a lot of. So I'm going to just sketch these. The first one we have seen, 1 over x, we called it the reciprocal function. It is a rational function. If I plug in 1, I get 1. If I plug in -1, I get -1. If I plug in 2, I get a half. If I plug in -2, I get -1/2. And if I plug in a half, I get 2. Or -1/2, I get -2. We have asymptotes for this at x equals 0 and at y equals 0. And these are things that we covered before a while ago. Actually, somewhat recently, we covered this in chapter 10, because this is a rotated conic. What's the conic section that this is? Hyperbola. It's rotated how many degrees? Look at it. 45. It's rotated 45 degrees. So now what happens if we take that basic equation, 1 over x, but we do 1 over x squared instead? So x still can't equal 0, so that is an asymptote. And there's no x value that I would plug in that I could get y equals 0. That could not possibly happen. So y equals 0 is still an asymptote. If I plug in 1, I get out 1. If I plug in -1, I get out 1. If I plug in 2, I get out a 4th. If I plug in -2, I get out a negative, or I still get out a 4th. If I plug in a half, I get 4. Or if I plug in a -1/2, I get 4. So like everything I'm plugging in is turning into being positive. So it's, kind of like when we have parabolas and you have x squared, it's always going to be positive until we put like a reflection on it. And then it can be reflected down. If I reflect 1 over x, it would be in the other 2 quadrants if I reflect it. What's going to make the asymptotes move? Gavin? Translations. Up or down, left or right? Yes to all? Yeah. So if we took like 1 over x minus 3 plus 4, I don't know, I'm making up numbers here. This would be a translation to the right 3, so that x equals 0 would now be at x equals 3. And up 4, so now I would have a y asymptote at 4, and then we would just have that same graph, those branches in here. Right. Okay, there's something, there's a theorem, limits at infinity theorem, which we might refer to as the little big theorem, little over big theorem. Okay, so the actual calculus theorem is sitting right there, but I'm going to just give you like 2 examples. The first one I'm going to do right above the word little over big. So I'm going to talk about the limit as x approaches infinity. So let's say 2 over 10. And then 2 over 100. And then 2 over 1,000. And then 2 over 10,000. Two over 100,000. Do I need to keep writing, or do you guys get the pattern? You get the pattern? What y value are we approaching as my x values go to infinity? What is it? It is 0. Because if I have a little number on top, and then the bottom number is getting bigger and bigger and bigger and bigger and bigger, it's just getting smaller answers. And it's just eventually going to go to 0. What if I went to like negative infinity? So if I had like 2 over negative 10, or 2 over negative 100, or 2 over negative 1,000, or 2 over negative 10,000. What's happening to my answers? If they're all negative, we're still getting closer to 0, just from the bottom. Okay, so these are still equal to 0. So this is what the little over big theorem is saying, or if you want to use the actual calculus theorem right here, it's saying as x approaches infinity, when we have some constant over x to a power, it's always going to go to 0. And that's the same for negative infinity. Now, if I have, let me find my equation. So the part I'm putting underneath there is an equation. Here it is. If I want to use this theorem, but it's not so like obvious that it's a number over x. So I have limit as x approaches infinity. And then my equation is going to be 3x squared minus 6x plus 1 over 2x plus 9. So right now I can't really tell to be able to use the big little over big. So we have a theorem that is related to this. I mean, it's not a theorem. This is the theorem, but I have manipulation. That's what I have. I have manipulation. So what I'm going to do is I'm going to take this equation and I'm going to multiply the top and bottom number by a value of 1. But my value of 1 is going to be 1 over, and it's going to be the highest power of x that I have here, so x squared. So I'm not changing the value of my equation whatsoever. I'm just making it look a little different. So I will have 3 minus 6 over x plus 1. And then I will have 2 over x plus 9 over, oh, not plus 1. Sorry, 1 over x squared. Let me rewrite that. And 9 over x squared. Okay, so I haven't changed the value of my equation. I just made it look way more complicated. And now what I'm going to do is I'm going to use this limit on kind of these individual pieces, the individual terms. So I'm going to look at just 3. If x is getting closer to infinity, that does not change the 3 at all. As x is getting closer to infinity, we've got this minus 6 over x. What will 6 over x be getting closer to? As x gets closer to infinity, what's happening to 6 over x? So it's going to what? It's approaching what number? 0. And this one right here, 1 over x squared. If I plug in any number for x and I start plugging in bigger and bigger and bigger numbers, this one's squared. So they're just going to get bigger faster. So 1 over some very large number is going to be 0. 2 over x is going to... Did I copy it wrong? I copied it wrong. This is 2x squared. Sorry about that. There's something didn't seem right. Okay, back to what we were looking at. So now the 2 itself, there's no x in that, so it's just going to be 2. But then adding 9 over x squared, that's going to get closer and closer and closer to 0. So the limit as x goes to positive infinity is 3/2. Now, I could try that with negatives as well. I could do negative infinity, but that's not going to change any of these answers. And it's not going to change 3 or 2 either because those don't have x's. So the answer is going to be the same for either infinity. Yes, Sam. I need to give you a pass. All right, finding asymptotes. We're going to find some asymptotes for today's rational functions. Here's a picture where I have drawn an asymptote. It's at a, x equals a. My limit for vertical asymptotes will always be a plus or minus infinity from the right. It will also be a plus or minus infinity from the left. Now, I don't know which one it is. That just kind of depends on when we plug stuff in and find it. But it will always be, if it's a vertical asymptote, you're always going to get a positive or a negative infinity as your limit. Okay? And then here is an actual example where I can show it to you. If I look at this equation, 3x minus 5 over x minus 2, where's the vertical asymptote? What can x not equal? So I drew that for you already. So now you will see that this is set up the way that I was doing kind of some of those examples on the very first page. This says x approaches 2 from the right. So somebody give me an answer of 2, but like to the right of it. Somebody give me a number that's close to 2, but to the right of it. Tyler. Even closer, but 2.0001 or something. Yeah. So what we're going to do is we're going to plug in. And we're going to see what we get. So I'm plugging in 2.0001. On top, I'm going to get 3 times 2.0001 minus 5. On the bottom, I'm going to get 2.0001 minus 2. Now, I don't actually care about the number. I care about if it's going to positive or negative infinity. It's going to go to one of those. So I really care about the signs. So the first thing I need to know is 3 times 2.0001, or whatever number you chose, take away 5, is that going to be a positive number or a negative number? Positive, because 3 times 2 is 6, and this is bigger than 6, so that'll be a positive number. In the denominator, if I take 2.0001 and then we take away 2, what kind of number do we get? Positive number. So this limit approaches positive infinity. So in my graph, when I find more information, I'll be able to have more of a graph. But in my graph, I know for sure that on the right, the graph is approaching positive infinity for the y. You see where I drew it on the graph? In black? And we're going to do the same thing for the limit as x approaches 2, but from the left. So let's plug in 1.999. So 3 times 1.999 minus 5 over 1.999 minus 2. On top, what does 3 multiply by? Sorry. What does 3 multiply by so that it equals 5? Like what number would go in this spot so it equaled 5? Do we know? 3 times what number equals 5? Do we know? It is 5/3, which is 1.6 repeating. So I'm plugging in 1.9. Is that going to be a positive or a negative number when I subtract 5? Do I? If I multiply either of these numbers by 3, this 3 times the 1.999 is still going to be bigger than 5/3. So that's telling me this is a positive. What about in the denominator? Bless you. Denominator. 1.999, take away 2. Negative. So this is approaching which infinity? The negative infinity. So on the left side of the graph, my graph is going to be going down as it approaches the asymptote. So you're not going to have a calculator to know what the graph looks like. You got to use things like limits to figure out what the graph looks like. For finding horizontal asymptotes, this is actually supposed to say X. When I copied it, I forgot to change this letter. Sorry. I should say X. We're going to do where we are finding as X approaches infinity. So that's where we were doing the little over big theorem, where we're going to plug in bigger and bigger and bigger numbers to see what it's actually approaching. And what that number is approaching will be the horizontal asymptote. Okay. So here's some information about rational functions. Rational functions can be written in the form of the function is equal to a numerator function divided by a denominator function. So it's like a function divided by a function. One thing that is important is that the denominator is not 0 and that the numerator and the denominator do not have any common factors. So on that example where we crossed out the x minus 1s, that's because of this right here. We have to cross them out if they are the exact same thing. The graph has vertical asymptotes at the 0 of the denominator, the zeros of the denominator, which we should already know that. The next section is talking about the horizontal asymptotes. So these horizontal asymptotes, you can look at the equations and know what they are if you know this information. We are going to use that, but we're also going to use limits to verify and justify that we are correct. and to learn limits. Okay? So if, and I forgot to copy the, I wonder if it's still open. I forgot to copy, when I was copying from your book, the equation. I'll show you really fast, but I forgot to copy this crazy looking equation. Okay, so it's talking about N's and M's and A's and B's. I'll just tell you what it is when we write it down. I forgot to copy this. But it says if N is less than M. Okay, so N is the degree of the numerator. And then M is going to be the degree of the denominator. So we're going to look at the degrees of the top and the bottom. We're going to look at the degrees. And then there's this, oh, well, I'll tell you that when I get to question B. So when we look at A, if the degree on top is less than the degree on the bottom, the graph will have a horizontal asymptote at y equals 0. If the degree on top is less than the degree on the bottom. For example, 1 over x has a degree on top that is less than the degree on the bottom. Okay? So this had y equals 0 as its horizontal asymptote. Part B says if the degrees are equivalent. So this part right here, this is the leading coefficient of the numerator over the denominator. So I'm just looking at whatever number is in front of that first term with the degree. It would be y equals that number divided by that number. Okay? So if I have, I'll just make something up. If I had like y equals 3x squared minus 2x divided by 4x squared plus 9, we would see that the degree is exactly the same on top and bottom. So my y equals 3/4 would be the horizontal asymptote. And then the third possibility is that you have the degree on top greater than the degree on the bottom. If the degree on top is greater than the degree on the bottom, there's no horizontal asymptote. So those are your 3 options for horizontal asymptotes. There's also something called an oblique asymptote, but oblique is like the fancy mathematical mature vocabulary. We can also call it slant asymptote. It's not as fancy sounding as oblique, but it's not a vertical asymptote. It's not a horizontal asymptote. It's somewhere in the middle asymptote. We will have this situation if we have a rational function whose denominator is degree 1 or greater. So we have to have something down here other than just a number, other than just a constant. And the top degree is exactly 1 more than the degree of the bottom. So in this case, we have a situation where the top is exactly 1 more than the bottom. To find the slant asymptote, we use long division. So I'm going to actually divide these. I had to put a 0 in to make sure I had all my placeholders for my powers of x. We do x goes into x squared, x times, multiply that, we get x squared plus x. Then we subtract both of them. And I get negative 2x, and I bring down plus 0. And I didn't plan this very well because I wrote way too big. So then I divide x into negative 2x. I get minus 2. And then I distribute the minus 2, and I get minus 2x minus 2. Then I subtract them, and I get 2 as my remainder. Okay, we're not going to talk about it right this second because that's a much longer discussion. We don't have time, but you throw the remainder out. Just get rid of it. And then the slant asymptote is y equals the quotient x minus 2. Okay, so that was a very fast overview of the things we're going to do. Now we're just going to like utilize them the exact same way you do them in your assignment. So we're going to start with example 1. The first thing I always do is see if I could factor it. Can I factor x plus 1 or x minus 1? No. Okay. Then I'm going to look for asymptotes. So I'm going to right away look at my denominator, and there's an asymptote. What can x not equal? -1. So x equals -1 is an asymptote. As I find these answers, I'm going to go ahead and plot them. So my domain are my x values. If x can't equal -1, then my domain's going to go from -infinity to -1 and union with -1 to infinity. How do we find x-intercepts? Always and forever. Marie, how do you find x-intercepts? Always, on every single equation you have ever had. I might need to factor. This one doesn't factor, so that's not going to help me. We need to find our x and y intercepts. Madeline, do you know how to find the x-intercept? Plug in 0 for y. Okay, so I will have 0 equals x minus 1 over x plus 1. I'm going to put 0 over 1. I'm going to cross multiply that. So I get 0 equals x minus 1. So x equals positive 1. One of my intercepts is at 1, 0. If you guys are sleepy, go stand up. Don't sleep through this. I know it's long. I get it. It sucks. But don't sleep through this. Megan, can you help me with y-intercept? What? Plug 0 in for x. So I'm going to have f of 0, and then I'll have 0 minus 1 over 0 plus 1. So I get -1. So my y-intercept will be at 0, -1, and I'll go ahead and plot that. Now we're going to use our limits to find how the graph approaches the vertical asymptote and to verify where we think our horizontal asymptote is going to be, which we haven't done yet. But we're going to use the limits to verify that and to help tell where the graph goes. So if I use the rules that I went over just a moment ago, and I look at the degree to find my horizontal asymptote, I have the same degree on top and bottom. If I have the same degree on top and bottom, then my horizontal asymptote is just y equals the leading coefficient on the top and the bottom. So y equals 1 should be my horizontal asymptote. Now we're going to justify that with limits. And then we'll also find the behavior at the vertical asymptote with limits. Is it -1 on top? Yeah. I don't even know why I ask questions when it's literally sitting in front of me here. Excuse me. All right, so we are going to find the limit as x approaches infinity. This right now is not in the form that I like it to be in. So I'm going to manipulate it, and I'm going to multiply the top and the bottom by 1 over the biggest amount of x's. So just x. So I will have 1 minus 1 over x over 1 plus 1 over x. So when I plug in infinity or just bigger and bigger numbers for x's, I'm going to get 1 minus 0 over 1 plus 0. So every time I see that little over big, that's going to become a 0. So 1 minus 0 over 1 plus 0 is equal to 1. And then we'll do the same thing for negative infinity. But I'm going to go ahead and use this one. So for this one, if I plug in negative infinity into the little over big, it still equals 0. So I'm going to get the exact same answer here. 1 over 1, or 1 minus 0 over 1 plus 0, which is still going to equal 1. If we have the limits the same, then I know that there is that asymptote there. And I've just justified what I had already found. So you will have to write down your limits so that you learn them. Okay? But also using the shortcut will help you learn that. All right, then we're going to do our limit around the x asymptote, the vertical asymptote. So we're going to do the limit as x approaches -1 from the left. And we're going to do the limit as x approaches -1 from the right. So we pick something close to -1, but on the left side of -1. So negative, anybody have an idea? Smaller than -1 on the left side of -1. Abby, give me a number. Perfect. I love it. Okay, so when I plug that in for my x's, I'm going to have on top -1.0001, take away 1, that's going to be negative. On the bottom, -1.0001 plus 1, what am I going to get? Negative. So we are approaching positive infinity. Negative over negative is positive. So in my graph, on the left side of x equals -1, it's going to be going up here. Now we're going to do the same thing, but for the right of -1. So maybe choose -0.999. So if I plug in -0.999 and then I take away 1, that's a negative number. If I put in -0.999 and I add 1, that's going to be positive. So we're approaching negative infinity on the right side. The right side, I had some points there. So since it approaches negative infinity, I know it goes down, and then the other, when it goes out to the end, it's approaching the horizontal asymptote. So I'll get closer and closer to that. And then in the other quadrant, I know it's going up, so it's got to be in this quadrant. And then it's got to approach the horizontal asymptote.
So the purpose of doing the x to infinity and x to negative infinity was to see.
That's to find our horizontal asymptote, but we already found it by a shortcut, which typically, if we had more time, you'd probably spend the whole day on limits and then the next day learn the shortcut. But we don't have time to do that.
And then, so then the next two, we're doing it off of the asymptotes.
The x asymptote, the vertical asymptote. So we can find out if it's going up or down. So when we do x goes to negative and positive infinity, we're saying if x's go this way or if x's go this way, what are the y's getting close to? The y's are getting close to 1. And then this one in the middle says, if we're getting closer to x equals 1, where the asymptote is, what are the y's doing? So we're always saying, where are the y's going? And then this would be where y is positive infinity, and this would be where y is negative infinity. But we're always talking about where the y's are going when we're doing limits. Okay? All right, so let's do another one. I'm going to see this equation, and immediately I say, factor it. Okay. So I took out a 2. I have x squared minus 9. I'm going to erase that because that factors further to x plus 3, x minus 3. And then x plus 2x minus 2. Nothing cancels. But now we can find vertical asymptotes. Vertical asymptotes. Where do I have vertical asymptotes? X equals -2, x equals +2. We've got 2 vertical asymptotes. Oh my gosh, I have such a silly question. Let's see if you guys can get it right. What if my x asymptote was at x equals 15? How would I graph that? Change your scale. Yeah? I know for sure that some of the graphs that you're going to get, 1 or 2 maybe, I don't know, are like pretty big numbers. So you might have to change your scale. So if you're doing it with the pen and you're like, oh, shoot, I should change my scale, it's easy to fix. Okay, because I have my x asymptotes, my vertical asymptotes, I can now talk about the domain, which goes from -infinity to -2, union, -2 to 2, union, 2 to infinity. So it's skipping over those asymptotes. We can find the x and y intercepts. And it really doesn't matter which equation you use for x and y intercepts or for a lot of the stuff. Sometimes it's easier to use the original, and sometimes it's easier to use the factored one. That's what you figure out as you're doing this stuff. So if I'm going to find f of x, f of 0, if I'm finding the y-intercept, maybe I'll use the original. 2 times 0 squared minus 18 over 0 squared minus 4. So I get 9/2. And then my x-intercept, I'll set 0 equals 2 times x plus 3 times x minus 3 over x plus 2 times x minus 2. Put 0 over 1, I'm going to cross multiply. I get 0 equals 2 times x plus 3, x minus 3. I'm going to solve that. I'm going to get x equals -3, x equals +3. Oh, did I put that one on the wrong axis, didn't I? Oopsies. Oh. Okay, what about our horizontal asymptote according to the shortcut? We're going to look at the degree. It's exactly the same. So what's my horizontal asymptote? Y equals 2. And now we'll justify it with limits. I'm going to use the original because when I justify this one with limits, this is the one where I want to divide by or multiply the top and bottom by 1 over x squared. So if we have a little number like 18, we divide it by x squared. As x gets bigger and bigger and bigger, this is going to approach 0. Same thing with 4 over x squared. So I get 2 over 1. My limit is 2. And then if I do negative infinity, and I'm going to use the manipulated equation. It's going to be exactly the same. This guy's going to be 0. This guy's going to be 0. So we get 2. So there I've justified my shortcut. And then we have to find the limit. We have to find the limits around the asymptotes so we know if the graph is going up or down at those vertical asymptotes. But there's 2 asymptotes. So we have to go on the left and the right of both asymptotes. So I'm going to have 4 steps for my limit for those asymptotes. I'm going to start with limit. X goes to negative 2 from the left. Then I'll do limit as x goes to negative 2 from the right. Then I'll do limit as x goes to 2 from the left. And then I'll do limit as x goes to 2 from the right. Now I'm doing something I should totally not do. I'm doing something right now that I should not do, but because I want to make sure you guys get enough practice, I'm not going to recopy that equation a million times because that wastes time in class. You shouldn't do that. You should copy the equation. Then we have to pick a number that is less than negative 2. So maybe negative 2.0001. I actually should have copied the equation once because I can't see it without zooming out. Let me copy it one time. All right, I'm plugging in negative 2.0001. Can't really plug it into 2. That's just positive 2. But I can plug it into x plus 3, and I get what kind of number, positive or negative, in x plus 3? Positive. I can plug it into x minus 3, and I get a negative number. In the denominator, I put it into x plus 2, and that is a negative number. Then I put it into x minus 2, and that is a negative number. So which infinity is this one approaching? Negative infinity. So on the left of negative 2, my graph is going down. So I can kind of fill in this side because I know it has to get closer to the horizontal asymptote also. Doing the same thing, only this time I'll pick something like negative 1.999. So I plug it in. You can't really plug it in 2. That's positive all the time. Plug it into x plus 3, and that's going to be positive. Plug it into x minus 3, that's going to be negative. Plug it into x plus 2, that's going to be positive, and plug it into x minus 2, that's going to be negative. So I end up with positive infinity. So on the right side of x equals negative 2, it's going to go up. Are you guys following okay? So then we have to check 2. So on the left of 2, how about just 1.999? So we'll have a positive number multiplied by, I will have a positive number multiplied by a negative number, divided by a positive number multiplied by a negative number. So that's going to be positive infinity. And then 2.0001. Zoom out, I can't see it all the way. I will have that 2 multiplied by a positive multiplied by a negative over a positive multiplied by a positive. So that'll be negative infinity. So on the left of x equals 2, on the left of x equals 2, it goes to positive infinity. On the right, it goes to negative infinity. And then I will just draw the rest of it using the horizontal asymptote. Now, I don't know if it's symmetric because I did not do any tests for symmetry. I don't know if it's symmetric, so I'm just doing a rough sketch. We could always test for symmetry if we wanted to know if they were symmetric. Okay? It's fun, huh? All right, next one. What should I do first? What should I do first? Factor it. Factor it. 2x plus 1 times x minus 3 over x minus 3. And the reason why I'm factoring first is because for this to be a rational function, we can't have any common factors in the top and the bottom. But we do. So what do we do to them? We cancel them. Now, this is actually important, though, because, you know, it's like 2x plus 1, but x cannot equal 3. This part right here is a hole in the graph. It's a hole. It's not an asymptote because it was in the top and the bottom. It's a hole. A fancier word or phrase for hole, a point of discontinuity. Okay, but that's just a hole. Now a hole is a point of discontinuity. Is x does not equal 3 a point? It is not an ordered pair. So what I'm going to do is I'm going to take that x equals 3 that I had right here, and I'm going to plug it in to the simplified equation. So we'll have 2 times 3 plus 1, which is 7. So my point of discontinuity, or my hole, is at 3, 7. So my domain skips over a hole. So we go negative infinity to 3, union 3 to infinity. There aren't any asymptotes. There aren't any, let me say that again. There aren't any vertical asymptotes because there's nothing left over in the denominator. And because there's nothing left over in the denominator, we actually don't really have a rational function anymore. 2x plus 1 is just a line. This is a line with a hole in it. So I don't have asymptotes. I probably have intercepts. Let's see. 0 equals 2x plus 1, so x equals negative a half. And then 2 times 0 plus 1 would be 1. I feel like I graphed this wrong in the other class. Maybe not. Maybe I didn't. So all I have is a line with a slope of 2 that has a hole in it. So I can't really apply limits either because it's not like approaching anything. That's when we have asymptotes. So we're done with this question. Okay, the next one I'm going to factor for you. If you had to figure this out on your own, you would have to use stuff from yesterday or last class's lesson where you have to like factor a cubic all the way. And we don't have time to do that today. So I'm just going to give you the factored form. So it's x plus 2, x plus 1 over x minus 2, x plus 4, and x plus 1. So we have common factors. I need to cancel those. Now we have x plus 2 over x minus 2, x plus 4. And what I canceled ends up being a point of discontinuity, except for it's not a point yet. X equals negative 1. So I need to plug that in. And so I get negative 1 comma negative 1/9. So that's my hole. Now there's actually some asymptotes on top of there being a hole. There's still numbers in the denominator or variables in the denominator. So we have asymptote at x equals 2 and x equals negative 4. When I write my domain, the domain has to skip over asymptotes and the hole. So I'll go from negative infinity to negative 4, union negative 4 to negative 1, union negative 1 to 2, union 2 to infinity. There's kind of 4 little sections of that graph. let's see, intercepts. If I plug in 0 for x, my y-intercept is at 0, -1/4. And if I make it say equals 0, do you guys notice a shortcut I could do when I say 0 equals x plus 2 over, anybody see a shortcut I can do yet? I can't hear what you're saying. I don't even know who was talking. Oh, the numerator equal to 0, is that what you're saying? Yeah, if I cross multiply, that denominator is always going to be multiplied by 0. So if you can remember to do it, we don't even need that. So x equals -2. So I'm going to use my limits to find the behavior around the asymptotes and the, oh, I didn't do my y. I didn't do my y, my horizontal asymptote yet. By using the shortcut, I'm looking at the degree on top and the bottom. The degree on top is 2. The degree on the bottom is 3. If it's bigger on the bottom, then it's y equals 0. So now I'm going to do the limits. I am using the simplified equation, but I'm going to take the denominator and multiply it back together. So I'm going to have x squared plus 2x minus 8, because it's easier for me to do it when it's multiplied together. Oops. Wait, was it? Now I forgot which one it was. Was it plus 2 or minus 2? Plus 2, okay. So this is the kind where I'm going to multiply everything by 1 over x squared. As soon as I do that, I'm not even going to finish. I'm not even going to finish, because on top, I've got little over big, which is 0. On the bottom, or not on the bottom, on the second term, I've got 2 over x squared, little over big, which is 0. And 0 over anything is 0, unless it's 0 over 0. But it's not, because there will be a 1 plus 0 down there. So this is approaching 0. It will be the exact same for the negative infinity. So what that is telling me is the very ends of the graph are getting closer and closer and closer to y equals 0. That's telling me the very ends of the graph. This is the end behavior. When I, oops, what did I do? Did I close it? No. When we talk about approaching infinity, we're talking about at the end. Okay? Then we'll do the limits for the asymptotes. So here's where I'm going to use a number that's just less than -4. So -4.0001. On top, that's going to be a negative number. On the bottom, negative number multiplied by a negative number. So that is approaching negative infinity. I will use negative 3.999. And now I'm starting to cheat because of time. I can still see the equation. I just don't want to waste your time. So if I put negative 3.999 in, I've got a negative over a negative multiplied by a positive. So positive infinity. If I put in 1.999, I will have a positive over a negative multiplied by a positive. Is that right? Did I do that right? Yeah. And then for putting in 2.0001, I will have a positive over a positive multiplied by a positive. So to the left of negative 4, we're going down. To the right of negative 4, we're going up. To the left of 2, we're going down. And to the right of 2, we're going up. So that was a total rough sketch, just using my limits. Like, I don't know exactly what points it's passing through at this moment. Do you guys see how it passes through the horizontal asymptote? So it's allowed to do that. When we are finding the horizontal asymptotes using limits, we're only finding what happens at the end. We're not finding prior to the end. We're finding what happens at the end. So it can pass through, which is why we need those other limits. You guys have questions? Like, I've done it a few times now.
So you were able to cross because it's telling you the end or not the
Yeah, because the horizontal asymptote is telling me what's going to happen at the ends. It doesn't tell me what happens in the middle. But you never, ever, ever can cross the vertical asymptotes. That's never a thing. It's sometimes a thing that you can cross the horizontal. Okay? These just require practice. I'm going to try to get through bits and pieces of the rest of it. I do not think I can get through like every single part of the rest of this. Okay? So I'm just going to try to get through a couple bits and pieces. So for this next one, we're definitely going to factor it. And I'll have x times x minus 1 over x plus 1. So we would have none for point of discontinuity. No holes. We do have an asymptote at x equals negative 1. And that means that my domain is going to go from negative infinity to negative 1, union, negative 1 to infinity. So if I find the y-intercepts, I plug in 0 for x. I get 0 for y. And then if I plug in 0 for y, I get 0 and 1. So I'm going to use the shortcut to figure out my horizontal asymptote, and we have a bigger power on top. If there's a bigger power on top, there is no horizontal asymptote. But if there is a degree starting at 1 or higher on the bottom, check, we have that, and the degree on top is exactly 1 more, then we will have a slant or an oblique asymptote. To find that slant or oblique asymptote, we have to use long division. This is the exact same question I already did the long division with, okay? So I'm not actually going to do it. It ends up being x minus 2. We already did it. So y equals x minus 2, I'm going to graph like as an asymptote, dashed lines. So when I go to do my limit, as let's do like x approaches -1 from the left, I could plug in -1.0001. I'm going to get a negative number multiplied by a negative number divided by a negative number. So negative infinity. So it's going to be going down here. And then it will use that oblique asymptote. And then I'll do the same limit, but to the right. So I'll do negative 0.999. So that will be negative multiplied by a negative divided by a positive. So positive infinity. So I'll make sure that this graph goes to positive infinity. And then it uses the slant asymptote. That graph's going to look like that. Hyperbola. Rotated hyperbola. You guys are hanging on. Barely, I know, but you're hanging on. I didn't even get to this one in my first class, so this is the last one. We'll factor it. X plus 4, x minus 2, over x minus, oh, that's not it. Oh, I copied it wrong. Hold on. This is not the right equation. It should be a 9 right here, not a, wait. Where did I get a 5 from? Oh, because I can't read her handwriting. You want to hear something crazy? This is pretty crazy. The notes that I was looking at for what I'm supposed to teach you guys came from my high school geometry teacher, my freshman year. That's a very long time ago. I mean, this wasn't necessarily from 1991, but I just think that's pretty crazy that I'm using her notes. But her handwriting I cannot read. She's a wonderful person. She was a wonderful person. Ready? Okay. Point of discontinuity. Do we have one? No, why not? Nothing canceled. Good. Asymptotes. Do we have any x vertical asymptotes? X equals 3. So the domain will go from negative infinity to 3, union 3 to infinity. Intercepts, the y-intercept would be negative 8 over 9. So 0, negative 8/9. X-intercept, we would have negative 4 and 2. I don't know why that keeps happening. The horizontal asymptote. Horizontal asymptote. Use a shortcut. Horizontal asymptote. What's it going to be? Sanjay, you know what it is?
2.
It's not 2. So if the degree on top and the bottom are the same, we're going to use the leading coefficients. So what should it be? 1. 1 over 1 is 1. So go ahead and graph that. We can justify that with limits. Probably not going to, because maybe if I have time, I'll throw it in the video. But so now I need to do the limits around the vertical asymptote, x equals 3. Maybe I'll have time. So something to the left of 3, 2.999. So I'm going to plug in 2.999. I'm going to get a positive multiplied by a positive. And then I have a squared down here. So I don't even have to, I don't have to plug something in at all. If I have a square down there, what's for sure happening? Positive. I don't even have to think. So this one, I'm not even thinking. I didn't even have a number yet for the next one. I'm not even thinking. The bottom is going to be positive for that one. So the first one is approaching positive infinity. So now I'll choose 3.0001. On top, we'll have a positive multiplied by a positive divided by a positive. We get positive. So both of them are approaching positive infinity. So this graph is going to have to pass through the horizontal asymptote in order to do that. And then on this side, it's got to be positive as well. Okay, and then we should in our assignment justify the horizontal asymptote with the limits, but I'm gonna just stop because that was our last example. Should I stop?
Yes.
Do you know how to find the asymptote? Well, yes, the answer is 1. I meant with limits, sorry. All right.